The unbalanced forces are transferred to the foundation. Okay, so isolation of machine from the foundation so that no heavy vibrations are transmitted is known as vibration isolation. So this process of isolating the vibration and preventing them from getting transferred to the foundation is called as vibration isolation. So what we did, we prepared a model of a rigid foundation. So this foundation is rigid foundation. This is isolator. The foundation is rigid. Later we'll see, we'll do the modeling of a flexible foundation also. But right now in this chapter we have considered only the rigid foundation. Okay, and so here is a machine to this a harmonic force is applied, and in between the machine and the foundation there is an isolator, and that can be mathematically modeled the spring mass and damper system. The isolator will have some stiffness as well as some damping properties. Okay, examples of the isolators are rubber, felt, or metallic strips. Okay, all these can serve for providing stiffness as well as damping. Okay, so the force transmissibility is defined as force transmitted to the ratio of force transmitted to the impressed force. Okay, that is Ft by F0. All right. So if I draw the free body diagram of the spring forces and the damping forces and write the governing differential equation, this is the equation which we get. And these forces, equal and opposite forces, are getting transmitted to the foundation. Right? So this is the total force transmitted. And we constructed the vector diagram of this. All right, so we have the displacement, velocity, and acceleration vector, each separated from the adjacent one by 90 degrees. This velocity to displacement is 90 degree, acceleration to displacement is 180 degree. Okay, then because of this displacement, velocity, and acceleration, you have these forces which are induced in the system. Right. For example, the spring force is opposing to the displacement. The inertia force will oppose the acceleration, and the damping force will oppose the velocity. All right, and then we construct a resultant of this. So these are the impressed forces, correct, and these are the transmitted forces. So resultant of the transmitted forces is this hypotenuse of the triangle, and that is given as square root of kx square plus c omega x square, where x is the steady state amplitude, and that is given as ft by t square plus c square omega square. And another way to write the steady state amplitude is f0 by k 1 square root of 1 minus r square whole square plus 2 zeta r whole square. Where what is r and what is zeta? Can somebody tell me?
R is frequency ratio.
R is frequency ratio and zeta is the damping ratio. Okay?
Damping ratio.
So now this is also correct, damping ratio. So this is also steady state amplitude, and on the previous slide also we derived one more equation of steady state amplitude. So we compare this, equate both this. So now I am interested in finding the transmissibility ratio. That is Ft by F0. So I equate Ft by F0, that is the transmissibility ratio, to the rest of the terms. And when I simplify this, I get this expression for the transmissibility. Square root of 1 plus 2 zeta r whole square upon square root of 1 minus r square whole square plus 2 zeta r whole square. Okay. So that is the transmissibility ratio, mathematical expression for that. And the phase lag between Ft and F0 can be, we can get it from this diagram. So F0 is the angle that is phi. Phi is the angle made by F0 with the displacement, and Ft is the angle made by, alpha is the angle made by force transmitted with the displacement. So the phase lag between these two is this angle, that is phi minus alpha. Okay, so we have to derive the expression for phi minus alpha. So phi minus alpha is equal to tan inverse of 2 zeta r upon 1 minus r square minus tan inverse of 2 zeta r whole square, 2 zeta. Right? All right. Now after that we studied the characteristics of the transmissibility ratio versus frequency. All right. So and we studied the graph, and we studied various characteristics. And one of the characteristics which we found out is that all the curves which has transmissibility is equal to 1 pass through frequency ratio r equal to 0 and r equal to root. Right. So all the curves will pass through these 2 points. When damping is 0, transmissibility goes to infinity. Right. When damping is 0, transmissibility goes to infinity. As soon as you introduce damping, then the transmissibility starts to decrease and its peak starts to appear and its peak shift to the left. All right. And so we identified these three regions. One is the spring control region, second is the damping control region, and third is the mass control region. Okay, the spring control region is generally this. So I'll just go to that slide. These three regions were identified. All right, so these are the three regions which were identified. This is spring control region, damping control region, and mass control region. Okay, so if you see this. So as transmissive, so now one more point, important point is which we discussed was some amount of damping should be always provided to the system. Right? So can somebody recall why is that some amount of damping should always be provided to the system? See, if you see this graph in the mass control region, generally we will be operating in this red. This is the operating area. Okay? That is for high speed machines. Beyond frequency ratio greater than root. That is generally the area which most of the machines are operating. So, and as you can see, the transmissibility TR decreases with as the damping is decreased. So, when zeta is 0, the transmissibility is going to be minimum, right? So, in spite of that, it is important that you provide some amount of damping. Zeta cannot be equal to 0. It's a very important Viva question, very important question from the point of view of understanding this whole vibration control. So can somebody recall and tell me why zeta should not be 0 under any
So because before we reach the mass control region, the system has to pass through resonance.
Correct.
And
okay,
so zeta is equal to 0 to be
correct.
very high.
So if you see this graph, first graph for zeta is equal to 0, somewhere along from going from r is equal to 0 to the operating speed, the system will pass through a point where the frequency ratio is equal to 1. That means the natural frequency of the system is going to match with the forcing frequency. All right. So at that case, R becomes 1, and at that time the system will vibrate violently because there is no damping. Okay. So you will have transmissibility to infinity. All right. So such violent vibration will damage the machine. So that should be avoided at any cost. So some amount of damping is always provided to the system. Right. So these were some of the salient features of the transmissibility ratio versus frequency ratio. I have given elaborate notes on that. I have updated all the notes till date, till the lecture. Today is lecture number 19. So till lecture number 19, I have updated all the notes on your class materials folder. Refer those. If your examination is offline, it will be a big challenge. It is going to be a big challenge. So don't take a casual approach because everybody's keen on having this examination offline. Right? Nobody's satisfied with this online examination system. Right? So please do not take things lightly. And if you are not clear about anything, if you need some extra explanation, extra lecture, you should let me know. Something is not clear. And I've been giving you notes in advance so that you should have those notes handy with you when you are attending the lecture. Okay, and don't just be have this mentality. Okay, notes are given and my job is done. You should both read those notes, otherwise it is meaningless. Okay, so let's continue because we have a lot of stuff to cover. We are at good speed. Not an issue. All the contents will be covered. Do you have the syllabus? Has anybody gone through the syllabus of mechanical vibration?
Yes, sir.
You are aware, no? So many things are there. This is the fifth module. Right now I am working on the fifth module, second part. All right, so let's solve some examples on this. So first example, all of you have today's notes.
Yes, sir, we have received.
So I will just read the question real quickly. A machine of mass 1000 kg is acted upon by an external force of 3000 newtons at 1800 rpm to reduce the effect of vibration isolators having static deflection of 2 mm under machine weight and damping factor of 0.2 r. Determine the amplitude of vibration of machine, force transmitted to the foundation, phase lag and phase angle between the transmitted force and the excitation. So let's solve this example. So mass is 100 kgs. So let me summarize the data. Impressed force is F0. F0 is 3000 newtons. RPM is 1800. Stiffness, let me just write omega first. Omega, that is forcing frequency, is twice by n by 60. So that is 188.50 radians per second. Stiffness K is force per unit static deflection. 1000 9.81 divided by 0.002. So that is equal to 4.905 into 10 raised to 6 Newton. Omega n is square root of K by, that is equal to G by delta static. That is equal to 9.81 divided by 0.0. So that is equal to 70.04 radians. So frequency ratio is omega n is 2.6. So calculate the force transmissibility. That is equal to Ft by F0, and that is equal to square root of 1 plus 2 zeta r whole square divided by square root of 1 minus r square whole square plus 2 zeta r whole square. All right. So substitute all the values in this and find out the force transmitted. And post your answers in the chat box. Any questions, please ask me. 0.02, sorry, 0.002, 2 millimeters. Are you calculating? 6. Somebody has calculated. So it is a force transmitted is 696.4. All right. Now, what else is asked in the question? The steady state amplitude, right? So, how will you calculate steady state amplitude? X is equal to F0 by K upon square root of 1 minus R square whole square plus 2 zeta R whole square. Right? So calculate the steady state amplitude. Tell me the answer. You can post it on your chat. I hope you guys are calculating.
So it is 2.3 into 10 raised to minus 4.
9.66 into 10 raised to minus 4.
Correct. 9.66 into 10 raised to how much? 10 raised to what?
-7.
Minus 5 meters. So that is equal to 0.0966 or 967. 0.0967 millimeters. All right. Then next is the phase lag. So what will be the phase lag? That is phi minus alpha. So that is equal to tan inverse of 2 zeta r upon 1 minus r square minus tan inverse of 2 zeta r. So find out how much is that. Yes, what is the answer?
Sir, 1.14.
What is that? Phase lag?
Yes, sir.
That is in radians you are talking. Angle you have told me the answer.
Minus 56.88 degree.
Minus 56.886.
886 degrees.
So 5 minus alpha minus 56 point something 8 degrees. Okay. So is this answer correct? So mathematically you have got this answer, but is this answer okay?
No.
So why not?
Pi angle is larger than alpha.
Huh? So let's go back to the slide. Vector diagram. Okay. So this is the vector diagram. So what is leading? F0
F0.
and Ft. In that, what is leading?
F0.
F0. That is the impressed force is leading the transmitted force, right? And that is logical, right? The transmitted force cannot come before the impressed force. There will be some impressed force. After that, the transmitted force will follow, right? So if this angle is negative, then what does that mean physically? Correct? What does that mean? So if this is negative, that means the impressed force lags the transmitted force, which is not practically possible. Alright. So you are getting this negative because this angle is you are getting negative, right? So and this is also negative. So what we have to do? We have to add 180 degrees to it. So tell me this one is coming positive. This one is coming negative. So add 180 degree to this negative answer. First tan inverse of theta and tan inverse of 180 minus theta is same. So what is the value after you add 180 degrees? Yes, just add 180 degrees to your answer. That's it. Whatever answer you got, 53 point something, right? 53.8.
So 123.1.
123 point. So that is the phase. Any questions? We'll produce to the next example. Proceed to the next example. Next question. A 100 kg turbines operates at 200 RPM. What percentage of isolation is achieved if the turbine is mounted on 4 identical springs in parallel, each of stiffness 3 into 10 raised to 5 Newton meter? Right? This is the question. So let's summarize the data. So M is equal to 100 kgs. N RPM 2000. Omega N natural frequency is K equivalent by M. K equivalent is 4 times K is equal to 4 into 3 into 10 raised to 5. So it is 12 into 10 raised to 5 Newton per meter. Omega N is square root of K by M. So that is equal to 109.54. So now you have to find out the percentage isolation. So percentage isolation is 1 minus transmissibility basically, okay, into 100. So transmissibility is square root of 1 plus 2 zeta r whole square on square root of 1 minus r square whole square plus 2 zeta r. So nothing is specified in this example about the damping. So take zeta is equal to 0, right? And R will be the forcing frequency upon natural frequency. So find out R and substitute in the equation and find the value of transmissibility ratio. Percentage isolation will be 100 into 1 minus transmissibility. Hello, madam. Sorry about the interruption. All right. So what is the percentage isolation? Hello.
62.35.
62.3%. Okay. All right. Okay. So remember this correlationship between isolation and transmissibility. So isolation is 1 minus transmissibility, and percentage you just multiply it by 100. Okay. Next question. Any questions? All right. So let's continue. An air compressor of 450 kg operates at a constant speed of 750 rpm. The rotating parts are well balanced. The reciprocating part is 10 kg and crank is 100 mm. The mounting reduces a viscous damping of factor 0.15. The mounting introduces a viscous damping factor of 0.15. Specify the spring stiffness for the mounting such that 20% of the unbalanced forces is transmitted to the foundation are transmitted to the foundation. Find out the amplitude of the transmitted force. So let's again summarize the data. So mass is 450 kgs. Mass is 1750. Forcing frequency therefore is twice pi n by 60, so that is 183.26 radians per second. Reciprocating unbalance is 10 kg. So we haven't solved any problems on reciprocating imbalance, but indirectly you will come across this type of question. Eccentricity, crank radius is 0.1. Okay. Damping is 0.1. You have to find stiffness, transmissibility. What is the transmissibility ratio? Yes, can somebody tell me? So transmissibility ratio is equal to square root of 1 plus 2 zeta r whole square upon square root of 1 minus r square whole square plus 2 zeta r. Right? So find out r. So what is transmissibility ratio in this question? Hello.
0.2.
0.2. All right. So TR is 0.2. Right. So substitute transmissibility as 0.2. Zeta is given 0.15. Solve this quadratic equation and get the value of r square. Tell me the value of r square. Post your answers on the chat. Anybody is calculating?
Yes, sir.
7.402.
Correct. And the other answer is negative. So you get two. You will get is a quadratic equation of r square. Correct. So you get two answers. 1.402 and other is this negative. So this is to be neglected. Okay. So r is 2.721. So that is equal to omega by omega n, and omega is 183.26. Omega n is k by m. Find out the value of k. The value of k.
2.04 into 10 raised to 6.
Correct. 2.04 into 10 raised to 6. All right. So that is the value of stiffness. Next, we have to find out the force transmitted. So Ft by F0 is equal to the transmissibility ratio. And to find out F. What will be F0? Can somebody tell me? How much will be F0? What type of harmonic? What is the type of harmonic force discussed in this question? Yes, anybody? What are the various types of harmonic forces we have learned? First one is force directly attached to the mass, then rotating imbalance, support excitation, reciprocating imbalance. So in this this example is discussing what type of unbalanced force? Yes, anybody?
Reciprocating imbalance.
Reciprocating imbalance. Okay. So what is the equation for reciprocating balance? It is similar to the rotating imbalance. It is same equation, in fact, m0 into omega square into E, right? But here m0 is the reciprocating mass, which in our case is how much?
10 kg.
10 kg. All right. So substitute that in the equation, and you know omega, you know E, and so this becomes m0 omega square E. Find out F.
So 6716 Newton.
Correct. 6716. So that is just a round of error. I got it 6720. But a slight round of error due to the test. All right. Last question for today's lecture, and that will complete this transmissibility of rigid foundation. Okay. Last question we'll do. So static deflection of an electric motor of mass of a mass 500 kg supported by the system of 4 parallel spring and no damping is found is and no damping is found to be 60 mm. Okay. If the rotating imbalance is 0.2 kg, determine the amplitude of vibration of 2000 at 2000 rpm and force transmitted to the ground. So let's write the equation for this, that is the dimensionless amplitude equation. Dimensionless amplitude ratio. I hope you recall this term. Okay? So that is x divided by m0e upon m is equal to r square upon square root of 1 minus r square whole square plus 2 zeta r whole square. And so there is no damping, so zeta is 0. Right? Omega n will be square root of g by 10, and r is omega by omega n. What will be, and so find out r, substitute in the equation, and m is 500 kgs. Unbalance is given as 0.2 kg meter. So M0E is 0.2 kg meter. Delta static is 60 mm. So 0.06. You have R. Omega is how much? 2000 RPM into twice into 5 divided by 60. So you have all the quantities. So you have M0E, so M, you know R square, zeta is 0. So find out X. Post your answers on screen. Yes, anybody is calculating?
Sir, R equals to 16.38.
Correct. R is 16.38.
Sir, X is 0.0157 meter.
X is 0. Yes, X is how much?
0.0157 meter.
No. I just write the equation X divided by 0.2 by 500 is equal to 16.38 square divided by 16.
Sir, 4.01 into 10
Correct.
10 to the power minus 4
4.5 into 10 raised to
minus 4.
minus 4 meter. Correct. Correct. Or that is equal to 0.4015 millimeters. Right. Okay. Now we have to find out the transmitted. Calculate force transmitted. What will be the equation? Ft by f0 is equal to what? What will be on the right hand side? Yes.
1 by root of 1 minus r square the whole square.
So what is the equation? 1 plus 2 zeta r whole square divided by square root of, don't forget the equation, 1 minus r square whole square plus 2 zeta r whole square. This equation is for the dimensionless amplitude ratio. All right. So, and this is the steady state amplitude. Steady state amplitude should not be confounded by the terms. Right? And this is the equation for force transmissibility. Right? And that is ft by 0, and that is this equation. So in this you have to substitute zeta is equal to 0. So this reduces to what? This reduces to ft by f0 is equal to 1 upon r square minus 1, provided r is greater than 1. Right? And what will be f0? Yes. Just now we calculated that. This is what type of imbalance?
Rotating.
Rotating.
As well, reciprocating.
So equation is m0e omega square. So you know what is m0e, you know what is omega square. All right, you know what is r. So find out force transmitted. Tell me the value.
Sir, 32.82034.
32.82 newtons. That is the question. Right. All right. That's all for today. Any questions? We have finished 5 practicals for each batch. So 8 is the minimum required. So we will be first completing those practicals. There is one practical on the gyroscope. So that we will be doing.
Hello, sir.
Yes.
Sir, in the practical exam, do we have to go through only Viva, or we will be having any practical exam also?
No, I think it will be only Viva. Only oral exam will be there. But questions on practicals can be asked. You will not be asked to perform the experiment, but questions on whatever is covered under the practical session head, that can be asked, including the programming.
Sir, sir, if the exam happens offline, or
Huh?
something like that.
Pardon? I didn't get that last part. All right, that's all for today. Thank you. Bye.
Thank you, sir.